Welcome back, everyone. I was hoping to welcome you to session number 3 of CANE 2022, which has the title Training and Learning. This is a relatively long session. We have 5 papers, as I will try to show to you in just a minute. So as you can see here, we have 5 papers. The first is an empirical evaluation of flow-based programming in the machine learning deployment context. Andrei Palais will be the presenter for this paper. The paper is Automatic Checkpointing and Deterministic Training for Deep Learning by Xanjie Xu, Hongyu Liu, Guanghong Tao, Zhao Xuang, and Xiangyu Zhang. And I would like to understand who the presenter of this paper is, and if you could briefly mention that you are present.
I will present the paper. I'm Xiangzhe Xu.
Very good. And you're presenting, right? Excellent.
Yeah.
Thank you very much. I appreciate it. So you're here. The third paper is Influence-Driven Data Poisoning in Graph-Based Semi-Supervised Classifiers by Adriano Franchi and colleagues. Who is presenting that paper?
Hi. I don't know if you can hear me. Yep.
We can.
Okay, yeah, so
Excellent.
Hi, I will present the paper later on.
Excellent, very good. And then the fourth paper, and I hope one of the authors is there, is Engineering a Platform for Reinforcement Learning Workloads. It's an industry talk by Alicanso and Kinshuman Patra. Is one of those two paper? They will be there by the time is their opportunity to present. And then the fifth paper is Method Cards for Prescriptive Machine Learning Transparency by David Atkins and colleagues. Who will present this paper? Jeremy, are you the presenter?
Yes, I'm the presenter. Thank you.
Very good. Thank you very much. That means that we have at least 4 of the 5 presenters present. I will then stop sharing my screen. I think everyone knows the drill by now. Presenters get 15 minutes of time to present, and that includes potentially some time for questions, and then we will have a discussion at the end. And if the speaker for the fourth paper does not until then, time for discussion. I would like to the first speaker, Andrei Palais, I hope I pronounced that correctly, an empirical evaluation of flow-based programming in machine learning deployment context. So, Andrei, the floor is yours. You have 15 minutes.
Thank you, Jan. So I have I just like to mention that you can hear me and see the screen. You don't mind?
We can, and we can see it.
Perfect. Excellent. All right, let's get cracking. So thanks for the introduction, and hi everyone. I'm very excited to be a part of this conference. I think the software engineering for AI finally gets the recognition it deserves from the research community, which is great. So my name is Andrei, and I'll be presenting this work with my colleagues Christian and Neil. We are from the MLHCL group at the University of Cambridge. And we'll be looking at the deployment of machine learning and the flow-based programming. So to get started, let's acknowledge the obvious that you've all heard by now a million times, that we see ever-increasing adoption of machine learning year to year. And that's both across businesses as well as research. However, there are multiple reports and multiple surveys, again, from the industrial consultancy firms and from the researchers in the academia that show that there is a fair bit of challenges and difficulties in the deployment, and not as many projects are as successful as we would hope. That kind of sparked our interest is what would be the bottlenecks and what would be the potential problems that would lead to this kind of challenges. And we, based on our own industrial experience, as well as other works we saw and heard about, we postulated a hypothesis that might be, it just might be, that one of the problems could be the existing infrastructure that people are trying to deploy machine learning on. More specifically, there is a very well-known paradigm in designing software these days called service-oriented architectures. And while it's certainly great, and that's why it's probably de facto standard in the software engineering these days, as particularly its flavor of microservices, it might be the root of the problems some of the problems we see in the deployment. So to motivate this a little bit more, let me talk about this very simple example. So we have three services, A, B, and C, and B calls A to get some data, maybe get some processing going. A probably reaches to database, probably calls service C for some additional data that it needs, collates it all together, that's whatever processing it needs, and returns the answer to B. That's a very, very standard and common thing that you would see in microservice-based software. The problem comes where we're trying to build any kind of a model that somehow models the behavior of A. For that, we would need to collect a data set that represents the behavior of A. And that would mean we need to match all requests from B to all responses that B received, as well as all requests to C and all responses that it gave to A. If there was any kind of internal state, maybe database or memory or elsewhere, that would also need to be matched to that. And unfortunately, there is nothing embedded in the paradigm. I'm not saying this is not a problem you can solve. You can, but there is nothing embedded in the software-oriented paradigm that service-oriented paradigm that would help you solve this problem. So, so we have, if we agree that for three services is a problem, how about this? Where we have dozens, if not hundreds of services, which would be a case in reasonable scale enterprise systems. So we have this kind of thought that we've been thinking about for a while, and we thought maybe this is just our own experience in the industry, but no, apparently other industrial experts are talking about the same thing, and I particularly like this quote from Confluent, which talks about data dichotomy. So services are very well designed, scalable, and reliant, because they are all about hiding data behind the interface that they expose, while we currently live in this world where we feel the demand for data being explicit and obvious and clear and accessible and discoverable is very important. So this is a conflict that we are looking to resolve. We feel that we need data-oriented architectures to build modern software to answer the demands of the data-driven world. And while you could probably iterate, and there are attempts to iterate on the services for this, as a research group, we felt that might be a nice opportunity to explore other design paradigms. So particularly in this work, we focused on something known as data flow. So I should say that services is a kind of a representation of what is known as control flow, where you model the software as a logic and the sequence of operations of verbs, if you'd like. Whereas data flow is all about the incoming data, maybe like streams of data into the system, and the transformations, joins, that represent the business logic as the functions of data. And then you get the output streams or like flows of data. So that is a different paradigms. There are different ways of designing the same thing. You can build functionally equivalent systems. So this is what we would like to consider. Particularly, data flow is kind of very wide, but there is a well-known flavor of it called flow-based programming, first introduced back in the 80s by John Morrison, which we used as a basis for the study. And the nice thing about it is a couple of features like data flow graph or name ports that enable data coupling, which we felt were particularly important. So this is what we decided to evaluate. So how do we evaluate? How do you evaluate software design paradigm. So what we did, we came up with a couple of case studies which we implemented ourselves that are set. These are mini applications set in different business areas to kind of highlight the generality of data flow in its application. And for each of them, we formulated a business problem that could be solved using machine learning, which is what we did. With each of the applications, we went through the entire process of deploying machine learning to solve a particular business problem within this application. And our aim was to measure the evolution of the code base. As you would expect in a real, production environment, the code base changes as you deploy a new solution to it. So we wanted to measure its evolution to see how it is affected within a particular design paradigm. So for each of the case studies, for each of the applications, we maintain two separate code bases. One implemented with Dataflow, another as a baseline implemented, of course, with services, as this is we kind of saying the de facto standard now, so that's the only reasonable baseline for the study. And we recognize three stages that you would go through if you were a data scientist performing a deployment in production environment. So first is you have just a basic application. There is no machine learning, no nothing. It just fulfills some functionality. Then once you were tasked with a business problem, first step what you do is you would collect data and from the system. And in the majority of cases that I've seen so far, data set was never readily available, so data scientists would need to go in and actually collect the data. So that is the first step of the code base evolution. Then the something that you don't see here is a model training, and that's because in real life you would probably you would most likely expect that to be happening outside of your application. That says collect the data and then they go away and train the models. So we don't recognize it as a stage. But then once the model is ready, you need to host it somewhere, maybe do inference with it, and integrate it into this application. So that's a final stage. We use the goal question metric framework, which is a well-known framework for empirical studies in software engineering. So we use it as a way to evaluate, to evaluate the paradigms, both flow-based as well as service-based. And we use a couple of metrics that most of them are well-known metrics in the software engineering research community, to like as a ways to quantitatively answer the questions that we pose. So I won't go on the right here. You see an example of one of the graphs that we present in this paper. I don't want to load you with any kind of a specific metrics, data, and numbers and things like that. They're all in the paper, and the preprint is all available in the archive. But just a couple of high-level observations that I wanted to share. First is in terms of absolute code, in terms of absolute size, service-oriented code bases actually grew slower, especially for the data collection task. However, the changes were a little bit all over the place. You needed to be aware of the more part of the system. So we found that we felt that for long-term maintainability, data flow was great because it meant that the changes that had to happen at each stage of the deployment were much more localized, and we were able to, and few components changing means realize that you need to talk to less teams and you need to coordinate less to make things happen, which is great. However, as the first thing shows, we felt that because flow-based programming is relatively underutilized, not as well known, it needs high-level tools that are probably not as available as they are for services. As the software engineering community, we worked a lot on making services great and easy to work with, not so much flow-based applications. So that we felt it's the biggest thing that we could address if we wanted to to consider flow-based programming in a more general sense than it is now, which is admittedly a very niche paradigm at the moment. So a little bit of a summary here for you, and a little bit of links to contact information. And if there is any one sense that I want people listen to this talk to take away from it, is that we feel that data flow-based approaches deserve a much bigger and more general consideration from software engineering community, both research and industry, than it probably currently enjoys. That's it for me. Thank you, and we can open up for questions.
Very good. Thank you very much, Andrei. Are there any questions from the audience? We have a few minutes because I stole the first 2 or 3 minutes at the beginning of this session. You raise your hand or put up in other ways, just start talking. If not, I have a question. Oh, sorry, go ahead. Yes, go ahead, Alex.
Hi, Andrea. I have a question. It's a great talk. And I was wondering when the machine learning parts interact with the other part of the code base, like the traditional service or the database or some not data-oriented part of the system, would the flow-based diagram still can help the developer design the system?
So we felt that like one of the things that flow-based programming exhibits is something called data coupling, which some argue, particularly the inventor of flow-based programming argues that a lot, that this is probably the loosest form of coupling you can imagine, which means you can like embed your machine learning models in your existing solution with as little impact as possible on the other parts of the system, which we felt is great. It's not to say that the API-based or like interface-based coupling that services exhibit much worse, but like as far as the impact on the code base goes, we felt that at least in our study, flow-based is actually a little bit more beneficial in that case because of the data coupling.
Okay, I see your point. Thank you.
Thanks for the question.
Yeah, and already, if there are no other burning questions by any of the participants, I would like to thank Andrei for his presentation and remind everyone that we will have a discussion session at the end of this session. But rather than that, to on to the second paper at this point, which will be presented by Alex or Xianxie Xu. With the title Automatic Checkpointing and Deterministic Training for Deep Learning. So go ahead, Alex.
I'll share my screen. Can you guys see my screen now?
Yes, we can see your screen.
Okay, so thank you for the introduction and thank you for your interest in the topic. Today I'm going to talk about a more technical perspective of the machine learning problem. And first, I'm Xianzhe Xu from Purdue University, and I'm going to talk about our work on checkpointing and deterministic training. In this work, we propose an analysis that can help us modify the deep learning frameworks to support the deterministic training. And we also propose a technique that can support the checkpoints from where the developers can replay their training process. And this is a joint work with Hongyu Liu, Guan Hongtao, Zhou Xuan, and Xiangyu Zhang. And so we know that the deep learning models are playing a more and more important role in the life-critical tasks. Take the auto-driven car as an example. The camera sees a stop sign, and it feeds it to the deep learning model. The model is 99% sure this is a stop sign. Thus, it tells the control system to apply the brake. Unfortunately, this system is vulnerable to adversarial attacks. If an adversarial applies even minimal perturbations on the stop sign, they can make this stop sign an adversarial sample to the model. That means the model would mistakenly think this is a speed sign and tell the car to accelerate. In this case, a severe accident might be caused. To protect a model from adversarial attacks, one of the defense techniques is called adversarial training. Intuitively, adversarial training means to train the model with adversarial samples. For example, here we tell the model this is not a speed sign, it should be a stop sign. In this way, we hope the model could be more robust against the adversarial attacks. However, in the experiment, we found that the robustness provided by the adversarial training is non-deterministic. So we have a test model with an accuracy of 80%. This can largely protect the model from adversarial attacks. Nevertheless, when we deploy the model in products, we train the model with exactly the same program, with exactly the same data, and even with exactly the same random number seeds, but the accuracy could drop by 20%. In this way, the product model can still be attacked by the adversarial attacks. Even worse, the number 20 is unbounded. We never know how robust the product model could be beforehand. To solve this problem, we need to make the training process deterministic. That means if we run the same program for multiple times, we need to be able to get the same results for every execution. We propose a twofold solution to this problem. We first modify the deep learning framework to make them support deterministic training. And on top of that, we perform dynamic analysis on the training program and instrument these programs. When these instrumented programs are executed on the deterministic framework, they yield deterministic results for every execution. Moreover, we can make check programs and support replay the training process from these checkpoints. Next, I'll talk about these two parts respectively. Discuss about the deterministic training. To better understand the challenge of deterministic training, we first talk about the sources of non-determinism. There are two major categories of the non-determinism, the algorithmic ones and non-algorithmic ones. The former are non-deterministic algorithms controlled by the developer. For example, the dropout layers randomly set some neurons to 0. This randomness can be determined by fixing the random number seeds. On the other hand, there are unexpected non-determinism introduced by the architecture and the frameworks. This non-determinism cannot be controlled by the programmers. For example, some GPUs implement the floating point computation in a non-deterministic flavor. For another example, some frameworks non-deterministically select the primitive operations based on their profiling results. They tend to select different operations on different architectures because these different architectures support different operations in different performance. And admittedly, most frameworks and architectures provide good support for controlling the aforementioned non-determinism. But the problem of non-determinism is not fully solved. For example, some of the commonly used frameworks, like TensorFlow, cannot handle the non-determinism introduced by data parallelism. So what is the data parallelism? We know that to speed up the training process, machine learning models can process a batch of data at the same time. And for each data sample, the framework creates a scheduling unit for it. It's called a task. Then it dispatches these tasks to different threads. Note that all these tasks refer to the same model. That is, there is only one instance of the model during the one execution. To review the problem, let's zoom in a bit. Suppose that the model has a random number generator, and there are two threads trying to acquire the random numbers from it. And let's assume that the random number generator is going to produce the number A, B, C, and D. I will show two possible execution results to illustrate the problem of non-determinism. Let's look at the execution from the perspective of thread 1. If in one execution it executes a bit faster than thread 2, then it will be the first thread to request a random number from the generator, and thus the generator will give it the number A. Then thread 1 will perform the following computation with the number A and generate the results. However, there are other possibilities. This time, let's assume that thread 2 runs a bit faster than thread 1. The generator will then give A to thread 2. And then the next random number is going to generate is number B. At this time, if the thread 1 also requests a random number, it will get the number b in this execution. We can see that thread 1 gets different random numbers in different runs. Thus, the following execution result is also different. In other words, the execution of thread 1 is non-deterministic. The essence of the problem is these two threads have data rates on the global random number generator. Thus, to solve this problem intuitively, we introduce local random number generator for each thread. We first find the random number generator that are susceptible to non-determinism, and then we replace each use of these unsafe generators to thread local ones. Note that we seed the thread local generators with the ID of the data sample, and the ID of the data sample would not change among runs. Thus, we can guarantee that the operations for a given data sample will say exactly the same sequence of random number among different runs. Thus, the execution results would be deterministic. So far, I've discussed how we introduce thread-safe generators to support deterministic training on the deep learning frameworks. Next, I'll talk about how do we make checkpoints that can support faithful replay. The most important goal of making checkpoints is to faithfully replay the program from these checkpoints. For example, suppose the training program transits from state A to state B, and then from state B to C. We make a checkpoint at state B. That is, we save some program states in checkpoint B and hope to resume the execution from it. When we load the checkpoint B and continue the execution, we are expecting exactly the same state as state C. That is, we want to replay the training process from checkpoint B. Unfortunately, existing checkpoint techniques for deep learning programs cannot support such faithful replay. Let's take the following program as an example. It first initializes two variables. The first one is the dataset, and the second one is a random number generator RNG. Then the program iterates for 10 epochs to train a model. For each epoch, it first shuffles the dataset, and then uses the model to predict the dataset. After that, it takes the gradient of the model and updates the weight of the model based on the gradient. Finally, it saves the weight of the model and the number of epochs to the checkpoint. When we load such a checkpoint from file and continue the execution, the variables that have consistent states with the original training process are marked in green, and those have inconsistent states with the original process are marked in orange. We can see that since we have the state of epoch and model in the checkpoint, their state is consistent with the original execution. But on the other hand, in the checkpoint, the state of data and random number generator is missing. Thus, during the replay, they have different values with the original process. Thus, all the following computation involving these two variables would be inconsistent with the original process. A naive solution to this problem might be save all the program state in the checkpoints. This is feasible only for small variables, like the random number generator. For the larger variables, we cannot afford the cost. For example, for the data, we cannot do that because it contains all the dataset and its state is huge. To handle this problem, we propose a method called fast forwarding. Example, the variables are data and RNG. Then to rebuild their states, we rerun the statement that will affect their states. Here we can see that the statements marked in green will not affect their states, thus we don't have to rerun them. And the first statement, on the other hand, it shuffles the dataset and it have effects on the state of both data and RNG. Thus we'd have to rerun this statement to rebuild the state of data and RNG. The instrumented code are shown on the right-hand side. And during the fast forwarding, only the statements marked in yellow are executed. It simply shuffles the dataset. And we also insert an if statement here. It checks whether the saved epoch number is reached. If not, it simply skips the following loop body. And note that the major training time is used to compute the gradient and update the model width. That our fast forwarding technique skips these expensive operations, and we just execute the loop with almost the empty body. Thus, it should be fast. Now I've introduced the both parts of our system, and next I will talk about the evaluation part. To evaluate our method, we implement the method in a prototype called DE-train. And we validate it on 29 model training programs and make sure that it can support deterministic from the checkpoint. And then we measure the overhead introduced by DE-train. On average, it's 46 lower than the original program. The major reason is that we let the deep learning framework use deterministic algorithms, and these algorithms are slower than the non-deterministic ones. And space-wise, we introduced around 10 kilobytes overhead for the models written in PyTorch and around 500 megabytes overhead for model written in TensorFlow. The relatively large space overhead is caused by sometimes we mistakenly put in some data loaders in the checkpoints. And by more carefully select the variables to save, the space overhead can largely be reduced. And finally, we use DE-train to solve 3 real-world problems. We use it to debug an exceptional drop-off accuracy. And we also use it to achieve deterministic robustness for adversarial trainings, like we discussed in the motivation example. And finally, we use it to debug a numeric bug in the training program. And for more details, please refer to our paper. And thank you for your introduction. Please come to the discussion session if you are interested. Thank you.
Thank you, Alex. I really appreciate your presentation. We are a little bit short on time, but if there is anyone who has a quick question specifically on the paper, then this is a good time to ask it. Anyone who has a specific question based on this?
Yeah, if I can jump in.
Please, of course, Andre.
Yeah, so I was wondering on thanks for the interesting perspective of the multi-threading and how it can affect the training. I was wondering on the first problems that you talked about, the multi-threading and dangers of the random number generator. Do you think it could be also, like you solved it with the introduction of local generators? Do you think it could be also solved with some of the multi-threading tools or patterns, like, maybe just a simple lock?
Sorry, could you briefly repeat the question? You are talking about the random generator, right?
Yeah, so the random generator, you did you created small local generators per thread, right?
Yeah.
Like alternatively, it could be used as a a global one as a resource, and it could be just locked, unlocked, and there will be no problem of like sharing the resource.
Yeah. I see your point. You mean the global lock on the global generator, right? That could be the solution, and so that's when every thread wants to access the global generator, it first acquires the lock, and then it gets a random number, and then release the lock. But this would prevent the thread from parallelism. And in the machine learning programs, the GPUs, they have hundreds of threads, and this will run concurrently. If we have a global lock, then this thread will have to run serializably. And so in that way, the degree of parallelism would be decreased and the performance could be affected. So yeah.
Makes total sense. Okay, thank you.
Thank you.
Good. Excellent. Good. And with that, Alex, I want to thank you for your presentation. Thank you very much. I really appreciate it. To a continuing discussion slot 4 to 5. So with that, I would like to switch to the third speaker in this session. Adriano, I think you are the one presenting, so feel free to start sharing your screen and to come in. And the paper is basically titled Influence-Driven Data Poisoning Semi-Supervised Classifiers. With that, Adriano, take it away.
Yep, I'm just giving the necessary authorization for the screen sharing. Okay, all right. I need to restart the browser actually. So I'll be right away. Okay, maybe the next one can go on because I have to restart the browser, so the connection will be dropped now.
Okay. So Ali Kanso, let me just quickly synchronize. Ali Kanso, you are, I think, in the call now. Although he is not responding at the moment. Ali?
Can you hear me?
Hey, I can hear you. Ali, would you be able to present your paper at this point? So we swap your paper and the one by Adriano, because Adriano has screen sharing problems.
Oh, unfortunately, I'm in another meeting. I'm wrapping it up right now, so I might need 5 minutes. Is that okay?
Then we are not going to ask you to present at this point in time. Is this last? Is the presenter for the last paper cards in this call?
Yes.
Hello. Yes, there we have Jeremy. Jeremy, would you be able to present at this point?
Yes, I would.
Because then you will be the last presenter in this session, and then you swap with Jeremy. And then with that, I would like to introduce the third or the fifth speaker, depending on how you count, method card prescriptive machine learning transparency. So Jeremy, please.
Thank you. Let me get this in. It's this one. Okay. You can see my screen now?
It is coming up. Yes, we can see it. Thank you very much.
Awesome. Thank you very much. Hi, my name is Jeremy Sarek. I am a software engineer. I work on the responsible AI team at Meta. I'm one of the co-authors, and on behalf of the other co-authors, I'm here to present to you our paper today, Method Cards for Prescriptive Machine Learning Transparency. So our motivation for this is we've seen a rapid adoption of AI across a lot of different application areas, and the impact of AI on people and society is ever expanding. As a result, transparency in machine learning has become very critical to building trust and legitimacy. Our focus is to help the population of ML engineers and practitioners improve the transparency of their models. Let's give some background on what we mean by machine learning transparency. Transparency, basically we see 3 different ways to improve machine learning transparency. The first is through documentation. The second is through reproducibility. And the third is through interpretability. So what do we mean by documentation? Well, there's been a lot of existing work on ML documentation, and some are extremely well known. I'm sure people are familiar with model cards for model reporting, which came from Google Research, as well as data sheets for data sets, which model cards document how the model behaves after training, and data sheets gives you an overview information of properties of the data set, like how it was collected, what the label distribution is, etc. IBM has created AI fact sheets, which are very comprehensive documents that are similar to model cards, and very succinct documentation for data sets, data nutrition labels, which has been published by MIT and Harvard. So those are some of the documentation efforts. It's hard to say we've seen much of this at scale, but we do see some of it in industry adoption. So with all of these documents, it's descriptive transparency, focusing on, how the model behaves after training, how the data was collected, etc. And these are great documents, but to a machine learning engineer, they are not necessarily useful. It doesn't really provide the actual insights that a machine learning engineer would need to know to train the model or reproduce the model. That's where we noticed a gap, and we decided to look into prescriptive transparency. So instead of describing the system after it's been trained, we look at ways that we could prescribe ways to create and train the system. The goal of that is to increase the software engineering will be consistent, increase that we can openly discuss what parameters were used to train the model, make it easier to reproduce both internally and externally. So we also believe that this will reduce the amount of documentation needed to achieve transparency, because now we do have the prescriptive method as well as the descriptive method, but a lot of that information can carry over. So we call this approach method cards, and it's about communicating these key elements that are useful to ML engineers and practitioners that can be used at multiple stages in the development process, such as model training, testing, and debugging. So what's in a method card, and how does it differ from other documentation? Here's a sample template of what a method card could contain. We'd have basic method information, safety and troubleshooting. So if there's a common pitfall, if there's anything that might expose a weakness of the model, might expose a bias, might leak privacy, that would be documented so we can avoid them. Data preparation, extremely important, from the simple, like, what is the input tensor shape, through how do you normalize this? How do you sample this data set? What's the recommended batch size? What are appropriate data augmentation techniques? How do you create the test training split? We have another section on modeling and optimization. So what components are you using? What are your hyperparameters? What objectives or loss functions should be used? How should you initialize parameters? What regularization should you use? All of that stuff. How should it be parallelized? Another critical section here is method benchmarking. What performance metrics should you use when evaluating this model? That's not just necessarily, accuracy or PR curves, but all sorts of metrics. You could be looking at fairness metrics. You could be looking at compute and efficiency metrics. So detecting overfitting, etc. Also, we would have a section on interpretability. What kinds of processes or methods would be appropriate for interpreting this model? So there are a wide variety of interpretability algorithms, but which ones are appropriate for this, both with local and global interpretability? And lastly, a section on robustness. How does the model behave for out of domain? How do we detect model drift if you're using this method? So here's a concrete example of what a method card would look like. I'm not going to go into detail of this. You can see it in our paper, but this will give you can see some of the examples here. For instance, input and output format, we expect a certain, it's a 1280 by 840 RGB with integer values. And if you look at modeling, it's going to use a SSD multi-box architecture. I'll tell you what type of activation functions, what type of optimizer to use, etc. So one of the key features of method cards is that we envision them as being composable. I can take methods and reuse them to create even more complex methods. You can do this through a relational database or a graph database. So for example, single shot detection is a fairly complex method. Well, we might have a method on a generic CNN architecture. We might have another method on, built on that on computer vision using CNNs. We might have a separate method on fairness or bias mitigation for CNNs. And we should be able to compose these together, so that instead of having to create a new method card from scratch for single shot detection, we can just reuse the components that we have. So the SSD method card in this example is inheriting information from the CNN method card and the CV fairness method card. Applications. So documentation is great. It's even better if we can take actionable steps. So there are two applications for method cards that we foresee. The first is code generation. If we have a method that is specified in this detail, an ML engineer can select this method and have it generate code automatically. That code is agnostic to whichever framework or language you're using. So there would be a different code generator, for instance, for PyTorch as opposed to TensorFlow. It doesn't matter because the method would be the same. So ML engineer selects the method card once they've identified what they're trying to do. The code generator outputs model training code. Then an ML engineer would go through and review if there's anything that needs to be manually adjusted, and then the engineer would train the model. On the other side, post-training, we would have code verification. We can use that same detailed information to make sure that the code itself is correct using a static analyzer. And then after training, we can also analyze the model to make sure that everything worked, as the method was prescribed. So that is all for my presentation right now. So thank you very much.
Okay. Thank you very much for a wonderful talk, Jeremy. You're getting some applause from the audience, as you can see floating over your screen, I hope. Mm-hmm. We have for questions. So if there are any questions that people want to raise, then this is the time. We are running a little bit late, so we can also leave any questions to discussion session at the end. Jeremy, I a strong or some relationship to how people, when I was a lot younger, were using a kind of method cards for keeping track of which compiler version, which library version, etc., was being used when we were building traditional software in C++ and other contexts. But since Jane, one of the program chairs, just turned on her camera, I'm suspecting that she wants to ask a question before we move on.
I do. Yeah, first of all, that was a really interesting talk. Thank you. Okay, I've got a funny echo going on here. I just changed location. It's a really interesting talk, and I had actually kind of planned to ask you a question about composability, but then you talked about that, which was great. I have a question, though, about, I'll call it feature interactions. Okay. Currently, we've been training kind of a deep learning kind of pipeline. And we've observed that different parts of the pipeline improve performance, but when we put them together, it actually detracts from performance. And I wonder if you thought a little bit about this in terms of composability of your method cards.
Sure. That's a great point. We haven't put a lot of thought into that area right now. What I will say is that the method card would be written by a subject matter expert. So as we would learn from implementing the method, that SME could improve the method card as we learn. That's all I can say right now.
Okay,
but
great.
Yes, that's a great question. Thank you.
Thank you.
Excellent. Now, with that, I would like to thank Jeremy once again for a wonderful presentation, and I'm sure that there will be a lot more questions during the discussion part. And with that, thank you, Jeremy. I would like the next presenter, which is Ali Khan. Looks very comfortable, I'm happy to announce. And Ali will be presenting Engineering a Platform for Reinforcement Learning Workloads. So, Ali, please take it away.
Perfect. Thank you, Jan. So I'm hearing an echo. Do I have to mute something? Okay, it's gone. So let me start by showing a quick demo of a certain machine that we have. So this is a machine called Moab. It basically has a camera in the center of it. And the objective is to keep this ball centered on the plate. And it's using a reinforcement learning technology under the hood. So if I drop the ball, you can see that it's always centered in the middle of the plate. Even when I try to move it out, AI model inside is going to control 3 legs that we have under the plate. And those legs are going to make sure that depending on the angle of the plate, the ball is constantly centered in the middle. Even if I try to move it or shift it, we're going to have always a reaction putting back the ball in the middle of the plate. So with that, I would like to share my screen and start explaining how we made this possible and how we... I'm sorry, I'm getting permission issues. Do I have permission to share my screen?
Yes, you should have. You have to activate it in the browser, or the browser wants to. The browser wants to ask you for permission.
Okay.
And I earlier today had to try to share twice before it worked. So the first time it didn't, then the second.
Okay, getting a message. Please check the permissions in your browser.
Yes, that is a problem.
The screen could not be shared. Did you click cancel to share screen window? So what I'm gonna do, I'm gonna use a different browser.
Should we get another going first so you have some more time to set things up? Yeah, is that sorry?
I'm just not sure how to test the sharing after, so yeah. I'm not sure if it's gonna work or not.
Yeah, so let's just try to get it. If you, Lucy is in the call. Lucy, I think, if you could, Lucy, if you could, so one of the participants in the call is Lucy Ellen Vakatara, and I'm hoping that you can work with her to make sure that your screen sharing works.
Sounds good.
There's also a test room if you go into the socialize, so you could go there and test that and then come back.
And then I'm hoping. And then if we then move to who was the third presenter, was going to be the fifth presenter, but now is the fourth presenter. Adriano, feel free to also turn on your camera, and we're going to enjoy your presentation about influence-driven data poisoning in graph-based semi-supervised classifiers. And feel free to go into presentation mode.
Yep.
The screens,
sure,
because we are now seeing the presentation screen. So if you click on yes, perfect.
Okay.
Yeah. No,
Okay, sorry. Okay, good. So I'm Adriano Franchi, and I am a research engineer slash software engineer at the University of Luxembourg as part of the S&T lab. And I will go through the influence-driven data poisoning in graph-based semi-supervised classifiers that have been accepted to CANE 2022. Let me first go quick on the agenda of today. So we'll go through a quick introductory subject for some required, let's say, knowledge for this paper, then about the contribution, so what we proposed with my teammates the study, so how did we evaluate it, the result, how well did it work, and some take-hats for you and to drive the conversation afterwards. So let's go through the introduction a bit. So in the past couple of years, as more and more system relies on machine learning models, the question about model reaction against malicious attack have rise. And in particular, when speaking about malicious attacks, we can categorize them by their strategy. So first, strategy would be to target the testing set. So in other words, to fool the trained model by crafting particular test inputs. This is also known as evasion attacks. Then we can target the training set. So in other words, we will alter the training data to affect the testing performance, or as we can see, to actually shift the decision boundary. These kind of attacks are called poisoning. As you might think, poisoning is a bit more challenging, as it means to study the propagation of information through complex algorithm through a lot of iterations. Now, in particular, but not so uncommon cases, label data is quite expensive and quite hard to get, as opposed to the unlabeled data, which is cheap and quite freely available. To countermeasure this problem, recent studies and scientists have come up with the idea of using both labeled and unlabeled data to actually boost the model. These techniques are called among the semi-supervised learning types. In particular, a subcategory of semi-supervised learning algorithm are called the graph-based algorithm and rely on the idea that label information propagates through graph where nodes are actually samples or inputs. When speaking about semi-supervised learning, two aspects are important to mention. The first one is that there is a transduction phase where the label are assigned only to the unlabeled part of the training data. So there is no generalization. And afterwards, there is a step of induction where actual supervised classifier is trained from the inferred labels. So there is indeed a generalization to unseen data. Now, as I can imagine the same as you, the first question would be how the graph SSLs react to poisoning attacks that we have seen. But when speaking about poisoning attacks, a more deeper question would be actually how to poison the graph SSLs, which is introductory to our contribution. By reviewing the different settings of state of the art, we figured out that it was actually a combination problem. That is, we have to find the smallest labeled input subset to poison, such that the effect on transduction and induction is the greatest. By effect, I mean the classification error rate is the highest, obviously. Then by digging a bit deeper, the goal is actually to approximate the influence of the labeled input onto the unlabeled one using during graph SSL. to the end to select the smallest subset that poison together has the greatest influence in the label decision. Our solution is called Major Influential Range, or MIR. That is how many times a labeled input L gives more than 50% of the overall label information received by an unlabeled input U. For example, here with a quick toy example, labeled input L1 has an MIR of 3, and labeled input L2 has an MIR value of 1. Now, about the study. How did we evaluate how our approach is working actually? First, there has been a correlation study. So how well the MIR value actually correlates to error rate. How have we done that? So we have calculated the MIR value for each labeled samples. And we compared it with the error rate after individually poisoning each labeled input. Now, we had to actually, we wanted to assess the effectiveness of MIR-based attack into increasing the inductive and transductive error rate. And obviously, how does it compare to state-of-the-art methods? How we did that? First, we selected n-labeled inputs to poison according to the different methods. We ran the graph SSL. We report the transductive accuracy. That is the accuracy on the unlabeled part of the training set. We ran the classifier training, so we perform induction, and we report the inductive accuracy. Finally, as our goal was not to worsen the life of SSL algorithm, but to make it better, we wanted to search if the MIR value can be used to actually create or design countermeasures. How have we done that? We selected n labeled input to poison. So as from the previous research question, according to a single method, we apply different countermeasures from which one is based on the MIR value. We run the graph SSL and we plot the transductive and inductive accuracy to see if there is some mitigation of the effect. Here, we'd like to go through some subject and parameters that we used. So we ran our study based on the state-of-the-art experimental studies, also on two image datasets, well-known for two well-known image datasets, which are MNIST and CIFAR, and a text dataset, which is also quite known in the scientific community, which is RCV1. To match SSL problem, we had to split the training set into an unlabeled part and a labeled part. The labeled part is split according to a percentage of labelization, which took the value of 5, 15, or 25%. The poison budget itself is the percentage of the labeled part of the training set that we target to poison. So either we run the experiment with 5, 10, 15, or 25%. Then the classifier training algorithm to perform induction, where the pre-established random forest and multi-layer perceptron. And finally, the poison selection method that we used were the MIR, so our method, the state-of-the-art greedy and probabilistic method. Both state-of-the-art methods come from the same paper accepted in New RIPS 2019, which the title can be seen at the bottom of this slide, and I can repeat it afterwards if interested. Now, how well did we perform? First, on the correlation study, spoiler alert, it did work. So we had the medium high to high correlation when running this study. Here is a sample of the result. On the right column, we have the Pearson correlation coefficient. On the left side, we have the Kendall correlation coefficient, which are two pre-established correlation coefficient values and calculation. Obviously, all those values were associated with pretty low, inferior to 10 power of minus 5 p-values. So our results are quite statistically relevant, significant. Then about the effectiveness. On the transduction, our method is effective and beats both state-of-the-art. For example, with MNIST, by poisoning only 95 over 13,000 training inputs, we managed to get a 36% error rate, which is twice the probabilistic method and more than 10 times the CRITI one. On the induction, we are also effective and we beat both state-of-the-art methods. For example, on Cypher, by only poisoning 200 labeled inputs over the 10,000 training inputs, we manage an error rate of 43% as compared to probabilistic only 21 and greedy for 24%. On average, the MIR method is 5 times more effective than the greedy and 4 times more effective than the probabilistic one. Finally, how can it be used to countermeasure design? What we apply as countermeasure is first to check the inputs that were more relevant according to the MIR value. And the second one is to randomly label additional inputs. So spending time to additionally label inputs. And we find out that double checking based on MIR value was way more relevant and more effective to mitigate the effect. Finally, some takeouts for you today. First, and the most important one was that we actually formalized the concept of influence in graph-based semi-supervised learning. Number two, we have designed a novel and effective label poisoning attack based on this concept of influence. The third takeout is that we have actually conducted quite in-depth empirical study with more than 300 unique experiment combination. And finally, we have designed, based on this concept of influence, an effective countermeasures. And that's it for me today. I hope you will have questions. Thank you very much for your attention.
Thank you very much, Adriano. I really appreciate your presentation. You're getting some applause from the audience, which is really cool. Are there any questions that the audience has? Not all at the same time. I had a bit of a side question because we've been looking a little bit into learning and semi-supervised classifiers. Some difficulty getting of those algorithms even beyond a purely supervised learning algorithm that is trained just on the labeled data set. Can you say or share some of your experiences around that? I mean, you would assume that a model is trained based on inferred labels because it has more data would do better, but so far we have not been able to see that in some of the cases that we've looked at. Can you share some of your experiences in that context?
Well, to be honest, when I started this project on semi-supervised learning, I was more, I started it because I saw some, actually a paper that relied on drug effect prediction. That is quite common semi-supervised learning problem, because labeling those let's say those mix-up of drugs is quite hard and almost impossible in some case. And so I didn't thought about the problem on how semi-supervised learning could actually beat supervised learning, but how semi-supervised learning actually provides something that I don't know, that scientific or engineers or I don't know business deciders can rely on. So to be honest, I didn't study at what extent a semi-supervised learning problem can actually beat a supervised learning problem. So
yeah, Okay, so you don't have too much, you don't have any insights there, and that's fine. The interest, so thank you. If there are other questions, we can take them now, because the problem that I have is that I think that my last speaker, Ali Kanso, is not at the moment, nor do I have Lucy Lacatare, who I asked for help in this. Unless we can solve that quickly, I am afraid that we have a bit of a pickle. But let me start by thanking you, Adriano, for your presentation. Very interesting. I will take a minute to call Lucy to see what the status is. Not in this call. I think she is. I'll try to figure out who the speaker is before I start the... Oh, Ali is back.
Thank you. Yeah.
Ali, are you here? If you're ready, then you can dive straight in your presentation.
Yes, I got the support I needed. So
excellent. I'm happy to hear that.
Okay.
Sharing also works then.
I'm sharing my screen now. I'm sharing a PowerPoint presentation.
You are brilliant.
Yes.
Excellent. I can see it, so we're game. Let's go.
Perfect. So I previously showed just a simple machine doing some ball balancing on a plate. I hope everyone remembers that, but this is just to explain how this was done. So let me introduce myself. My name is Ali Kanso. I'm a principal engineer at Microsoft. This work is done in collaboration with my manager, Kenshuman Patra. And there are, a huge number of contributors, too many to name, but it's about a platform that we engineered for reinforcement learning workloads, and it can be extended to other types of workloads. And today I'm just going to talk about how we achieved that. So before I start, I think it's very good to give the super high level overview of reinforcement learning, where you're basically trying to train an agent to figure out how to behave in a certain environment. In that environment, the agent can perform actions. Each action will affect the environment state, and then the agent can see now the next state and propose a new action, and this cycle can go on. So the key word here I want to emphasize on is environment, because that environment could be a system, or for example, it could be a machine. So an example of a system, if we talk about spam detection system, that's a software system. Image recognition, and so on. This could all be categorized as system level. But when we talk about a machine, I'm talking about physical hardware, like the machine I was just showing, which is the Hello World example that we use in our platform. And both, whether it's a system or a machine, that environment can be either a real environment where the training is happening and actual sensor data is being fed back and the agent is acting on a real environment, or it could be a simulated environment. So think of a self-driving car, for example. A lot of the training might be happening really on actual roads, on an actual car controlling the steering wheel of that car. Or it can simply be simulated, like, for example, if you're doing a drone training into a certain environment, then that drone can be simulated using a flight simulator and 3D maps and so on. Now, in terms of the simulated environment, it can either be based on an actual simulator that is calculating the state all the time, or it could be based on previous available data, something like a lookup table. So you can check if you are in state A and you propose action X, you become in state B. And those are mainly the type of simulated environments that we deal with. So in today's talk, I'm mainly targeting this area here marked in yellow. These are the systems that we target in our platform. So the idea is, how do we move from simulation to real life? And this is just going backward here. So if this is the actual machine and it's balancing, for some reason, an egg here, then on the left-hand side of your screen, you will see that we are using simulators here. So this is simulating the actual machine, and we're doing training here. And for example, after a few hundred thousands of iterations of training, we can realize that the model is now ready, and we can take it from the from our platform and deploy it on the actual machine over here on the right-hand side. Now, in terms of real-world examples, we have multiple customers using this technology. I can name the ones that have been publicized already. So PepsiCo, for example, is leveraging this technology. If you guys enjoy eating Cheetos and you found that they have the perfect texture, spices, and it's the crispiness level, then you can partly thank us for that. So they use this technology to control the conveyor belts and other systems in their factories, depending on multiple external factors like humidity inside, the level of crispiness, the desired level of crispiness, and so on. So we're talking about here AI that controls machines and machines that produce products. So basically, this is what we're focusing on here. And this is why we are more targeting the machine teaching. We call it machine teaching. Under the hood, it's just machine learning deployed on actual machines. So if we look at the AI landscapes, just to clarify some terminologies I'm going to be using, we have the AI users, which need easy access to AI platforms that can abstract the AI underlying complexity. And by here, I don't talk about the end user. I talk about the engineers or domain experts that want to use AI to make their job more efficient, maybe easier, and so on. So if you're a person who's using voice recognition, you're an AI user, you might be using voice recognition to serve your customers, and those are the end customers. We have AI contributors. Those are the contributors of simulators or data sets, and so on. So their contributions may not be purely intended for AI, but it can be used by AI. We have the AI creators, which are the data scientists creating, enhancing the machine learning algorithms, and the engineers creating distributed systems supporting machine learning training and serving. So, and finally, we have the AI benefiters, and this is all of us basically. Today, we are benefiting from AI one way or another. So in terms of the chain of benefit here, we have AI contributors. They support AI creators. AI creators enable AI users, and AI users would serve AI benefiters here. And our platform fits in this area of AI creators. So we are the AI creators in this platform, and we are leveraging contributions coming from contributors as simulators. And we are enabling AI users or trying to democratize AI such that anyone, any user, any domain expert can use AI without having to really know or have deep knowledge of the domain. At a very high level, the way it works is as a user, you can interact with this platform through a web portal or CLI. A lot of things will happen at the back end, and eventually you're going to have a trained AI model. You can export it and you can deploy it on your machinery as you wish. So in terms of requirements, first it helps to understand how all the actors fit into the system. So this would be the system that's doing the AI model training. We'd have the contributors. They provide the environments for the reinforcement learning. Those environments, as I mentioned earlier, can be either simulators or data sets. So if you're engineering a platform, you start asking yourself, what do I need to offer for the contributors? How would those simulators look like? What technology under the hood they would be using? How do I serve data sets? How do I store them, and so on? If you are now, as a user, you want to be able to define your requirements for training and when to stop training, what's a satisfactory goal for training in an easy way. And finally, if you're a benefiter here, we want to enable easy way of serving those models, leveraging technologies, especially with IoT, because we're talking about machinery here. So Internet of Things technology can really help a lot here if you want to do the deployment in a transparent manner without you having to worry about the underlying details. So as I said earlier, now imagine you're an engineer and you're asked to develop such a platform. Where would you start? And let's start with the left-hand side of the requirements I mentioned earlier, managing simulators. So the requirements here is that our users can provide their simulators, and they can either host their own simulators or they can ask us to manage the life cycle of those simulators. And those simulators should be elastic because one model, one AI model, can use 1 or 1,000 simulator or more, depending on the simulator, whether it's a fast simulator or a slow simulator. So to speed up your training, you wouldn't want to wait for a simulator to calculate a state each time you give it an action. And if it's a slow sim, then you don't want to be waiting for that. So you might want to spin up hundreds or thousands of simulators at the same time in order to speed up your training. So what did we do in this case? We implemented 2 modes of execution. The first mode is managed mode, where we leverage Azure technology, cloud technology, Azure container instances, and we manage the life cycle of a simulator. So, but in that case, how do we know what the simulator is? This is where the user of the technology will provide a Linux container image. In that container image, it will contain that simulator, and with the configuration file, we would know what command to use to instantiate or start that simulator, and we'll take care of the rest. So we'll deploy it on our clouds. We will take care of failures if they happen. We will take care of logging, monitoring, telemetry. We will take care of scaling it up and down on demand when this is needed. Now, there's another set of customers that really don't want to put their simulators like their trade secret. They don't want to put it on a cloud. They want to keep it local. And for those ones, our support is limited. We just give them an endpoint of how to connect to our system and some secure tokens, and they can do that. Now, this is made possible through the use of a component that we added, which is a simulator gateway. So for security reasons, we don't want the training engine is our code, our technology running on our infrastructure. The simulators could be a client code. So instead of interacting directly with our technology, we define a gateway or a proxy, where the simulators connect to the proxy, the AI model connects to that proxy as well, and then the proxy will take care of translating this information between the managed sim or between all the simulators and the AI model. Another thing we do here is that we have another component, which is sim control. We control the number of instances, and this is depending. We have some intelligence in our AI in our training engine that can tell us if it can handle more simulators. If so, then we spin up those dynamically, or we spin them down dynamically. Now, in terms of supporting users of the technology, provided that now we have the simulators in place, we defined a domain-specific language called Inkling. And in this domain-specific language, I'm just showing a sample here on the left-hand side. You can see that you can define the iterations limit after how many iterations you would consider that training is complete. In here, you can define a goal state. And in this example, for example, you can state, my goal is just to have the ball in the middle of the device that I'm using, and I don't want the ball to fall off a plate. And you can define it at a high level here. We have another hello world example, which is balancing a pole, and then that balancing a pole, you can define what angle you want that pole to be at and what considers a failure state. And here I'm just showing an example where if the user enters something illegal, we automatically detect that and give them an error message of what's allowed and what's not allowed in this domain-specific language. Now, moving to the training environment, and I think this is the bulk of the work that we do in this platform, we had really 2 high-level requirements: make the training as fast as possible. And I put asterisks here next to fast because one training can last for hours or even days, so that might not be considered fast by many standards, but it's faster. It's as fast as it can be, depending on what we're training for. And the second thing is that it should be reliable. And if imagine you're training a model for 2 days and then a failure happened, you wouldn't want to restart from scratch, and you want a platform that can be as reliable as possible. So for the first requirement, which is scaling, depending on the algorithm, we experimented with multiple reinforcement learning algorithms. Some of them were on policy, some of them were off policy. And based on those algorithms, we can automatically determine whether we're going to use vertical scaling or horizontal scaling. And we do that through the use of a technology called Ray. I'm going to brush on it on the next slide. So in Ray, you can define actors, and those actors can be unit of computation that you can horizontally scale them across multiple instances. And this is what we do for horizontal scaling. For vertical scaling, we can just determine how many GPUs, CPUs, and memory we can increase during runtime. So I mentioned the Ray platform before. So Ray is really just a platform for distributed computing. It's an open source technology. It's mainly intended for machine learning workloads. And what you simply do here, you define the concept of actors and tasks. And once you define those, Ray scheduler can take care of scheduling on multiple Ray nodes and with a concept called workers. And you can define at the end of computation what to do with the results. You can aggregate them and so on. So basically, if you're using Ray clustering and if you're using Ray actors, your platform is already enabled for parallelization. You just need to take care of creating dynamically worker nodes and removing them at runtime. Now, in terms of scalability, really, scalability is something you need to look at it holistically. So you cannot scale one part of the infrastructure, forget about another one. For example, if you scale the AI training model and now you have multiple models running in parallel trying to train, and you have one simulator, that's not going to help a lot. So, for example, you need to scale simulators and you need to scale your AI engine. For our users, we could have up to thousands of users training thousands of models at the same time. So our cloud platform itself needs to be elastic and scalable. And finally, our components, like our control plane serving those models, our API servers, and so on, themselves need to be scalable based on the workload. So for scalability, we really take a look at this from a holistic point of view, like a 360 view of what we can do. And this brings me to reliability. I mentioned earlier what happens if you're training a model for 2 days and something happens, or you have to restart. Yes.
Can I ask you to wrap up because we're starting to run out of time?
Sure. I have one more slide, I guess. So in here, we just leverage common principles. If you look at the principles of high availability, mainly we have 4 pillars. We talk about redundancy, having multiple instances running at the same time, monitoring to detect failure, recovery, automated recovery, where you can recover from failure. And most importantly, here we have checkpoints. So during our training, we constantly take checkpoints of the model so that if a failure happens, we can revert back to the latest checkpoints. And we use multiple technologies for that. I'm not going to go through them one by one. We brush upon them in the paper. And finally, the last step is that now that we have trained our AI model, what do we do with it? And how did we choose to wrap it up? And for that reason, for that purpose, we have 2 deployment models. One would be the IoT deployment using the Microsoft Azure Cloud. You can specify where you want to deploy it. The other one is a raw container. And the machine that I presented earlier that was balancing the ball, that was it's a Raspberry Pi machine. We did a raw container deployment. We do it over the air using Wi-Fi. But this is just just a way to show how you can take an AI model, wrap it as a container image, deploy it on a hardware, and let it control that hardware. So in conclusion, we just wanted to democratize AI for maximum numbers of domain experts that can be using it. We design a platform that offers machine learning as a machine teaching as a service, leveraging reinforcement learning. For engineering, we made sure it was scalable, reliable, easy to use. The technologies under the hoods we used is cloud computing, Kubernetes for container management, and finally, we used Azure IoT for deployment models. For future work, we're looking at beyond actual simulators because you don't really always need an actual simulator. Sometimes a lookup table, if you have the available data, is enough. You can use accelerators where you have one simulator and you learn from that simulator using a neural machine learning model, like a neural network. And you don't really, if the network is learning from the simulator, it can replace the simulator or extend the simulator at some point. We're looking at actual world feedback because when you train something in a simulated environment, it might not act the same in a real environment. So we always want to bridge that gap between the two and expand our deployment models to deploy anywhere and not just IoT or containers. And that's it. Thank you.
Very wonderful, Ali. Thank you very much. We have time for maybe one question, if there is anything from the audience. And until then, feel free to stop sharing your screen, Ali, because we see a wonderful effect. Thank you. Is there any question from the audience around this? because I had one quick question, Ali, if you allow me.
Sure.
I mean, reinforcement learning is concerned with training on device. Yeah, but what I notice is that you mostly train during simulation, and then you deploy a static model. So the training stops after deployment in the real world. Are there any plans to bridge the gap between training on simulator and training in the real?
Yes,